So guys, let's open up HLS. You know the drill. Let's make a project. Uh, let's make a VAdd. It stands for vector add. We define a top function, and just as we have done before, I'll make two files and one test bench file. And please do not forget to make this as a Zinc 2 board project. Nice. Nothing is hard, right? For convenient, you guys made it, right? So let's just define the size of the vector, and I don't know, v add int a int b int c, something like this. Okay, I have just created a test bench, which looks fairly simple. So we will make two arrays of a size int array, and I will just put two times I and one times I. And if we add them together, we should have an array of three times I, right? Okay, this makes sense. This is a C program, right? So in our test bench, we want to see if vector add is working correctly. Fine, right? Oops, like this. Can anybody try to finish this? We know what we're making today, right? We'll make a hardware that adds two vectors. So, imagine you're just writing plain C code. What should you have here? What should you have here? All right, so it's like C programming. Mingo, what should they write here? Sorry? Yeah, it's just like add them, right? So how would you write this? Yeah, just like C. Okay, if you don't like it, I'll just ask ChatGPT. Okay. Let's go. Okay. Write me a C code that has two vectors in instance 2. Yeah, like why not, right? Just add this. With some blah blah blah. Yeah, we can just use this. So, okay. For int I for 0. Like this, right? Why do we have a syntax error? I don't know. Let's just run it. We have a test bench. Ah, okay. What have I done wrong? We add. We add. We add. What have I done wrong? PB. What? Sorry? Oh, sorry. Like I was using Python. I made some Python mistake. This is why you should not use Python. Anyway. Thing it works, right? Yes, you think about it, and it seems to be correct. That's good. So what do we do next? We have run this simulation. What do we do next? Students, what do we do next? We do synthesis, right? So I'll synthesize this. And we have an error. So error says that we have an access on variable B, which contains an array with a known size. Now, if this were to be just a plain C code, this kind of code does not matter. But you need to know that A, B, and C are actually the arrays that should be stored in the DRAM, but not in the IP for right now, right? which means that if you do not give information about how much size of the data we're reading, it cannot be synthesized. So what should we do? So are we fine at this point? Is everybody like with the simulations? Okay. Some students made a quick fix. Why can't we just use something like this? Right? But I will tell you why this not works. As you know, the operand of the voice is actually an interface, right? They should be transferred using an interface. So if you have this problem, you should see this. Let's see. We have an array, and what's the default type of interface for the array? AT memory, right? We assume that we have another IP storing the memory. In our case, we don't. We want to read data directly from the DRAM. So what should we do? Well, it seems that array we can use MAXI. So AXI string is the DMA, and I think we'll learn about DMA next week. So today we're not going to be using DMA. So our leftover choice is SAXI Lite and MAXI. But SAXI Lite is kind of a subset of AXI Lite. AXI, which is small and slow. The MAXI, which is the master AXI, gives the permission of the IP to fetch direct data directly from the DRAM. So today we would use MAXI. But how do we actually transfer data? Like, imagine we have a C code and you want to copy memory. What do we use? In C, we should copy memory. What do we use? In system programming. memcpy, malloc, something like that. The basic idea is that we tell the basic address, the pointer, location of the memory, and we give how much length we should read, and we should copy data, right? Meaning that we need an MAXI port and one more additional port that will send the pointer. So I know this can be confusing, but if you want to transfer an array, we need two interfaces. So first, we will make one MAXI port to read data from the DRAM. Secondly, we will make another interface, the SAXI Lite, so that we can send the pointer. Does it make sense? Okay, is everybody following me? Okay, how do we transfer data in C? We have the pointer and the length. So using the same methodology, we will make two interfaces. Okay? So let's go. First, we will make a port call of MAXI. Pragma HLS interface. MAXI port for A. And you have it for B and C. Oh, you have it in the header files? Okay. But actually, this is not enough, which means that no, bundle. HLS interface bundle. Sorry for this. No. What? Actually, if you look upon the data sheet of the AX interface, we have two more things we need to tell. First is the bundle, and the next should be the bundle rules. So we have something called a bundle rules. If you want to make an MAXI port, you need to give additional information about the bundle and the depths. So I want some examples. Yeah, port and bundle. If you look onto the, so in the options, you have something like this. We have bundle, channel, clock, depth, interrupt, latency, blah, blah, blah. And today, we need to use two things, which is offset and bundle. So if you look upon the offset, controls the address offset in AXI light, blah, 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 for the specified port. And for the MAXI, generate an offset port and automatically map it to an AXI for light slave interface. Meaning that if we create an MAXI port, we can automatically create another AXI light port that we can send the pointer. So let's try that. And we have something called a depth. A depth is maximum number of samples for the test bench to process. So if you want to do simulation, we just specify a depth. This is kind of big enough to store the whole data. In our case, our array is 16 elements, so I'll just make it 20 to ensure it's big enough. Let's do the same. And as I mentioned, if you create an MXI with the offset of slave, we have additional SAXI light port. So in our IP block level design, I want a single AXI light port. If you want to do that, you can just create some bundles. Bundle CTRL means that we will bundle a bunch of ports into the same AXI light interface. And then don't forget that we actually have one more called a return. Let's see if it works. I think it works. And synthesize this. Oh, it works. If you don't understand about a bunch of AXI light and MAXI, we will get onto this after we create your block design and actually use it in Python, so don't worry. So if you reach this point, we can figure out that, oh, we take 198 cycle. Okay. And if you go to the analysis, wait, are we fine here? Is everyone following? Oh, sorry. Yeah. So can anybody synthesize this? And tell me if you can synthesize this, yes? What we did, great. 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 So if you see the latency, it's actually 198 cycles. And if you go on to see the what is happening there, what? Okay, so we're back. So what actually happens behind here is that you read a memory. In reality, this should be the pointer, the base offset of the memory we are reading. And then we'll have a write request. And we have a bunch of comparators and incrementers, which is basically the entire of the for loop. And then we read the values, we add them and write it. Fairly simple, right? So, question. How can we improve this design? How can we make this faster? And the last time, in the lectures, we have discussed about pragmas. What have we learned? Well, unroll, pipeline, data flow. And how should we improve this design? How should we improve this design? Well, you can basically parallelize it, right? So you imagine we have a single adder in our hardware. So which means that if we have 4 adders, the hardware should be 4 times fast. So how do we do that? We actually write the pragma HLS unroll. So if we do not specify the factor, it will try to completely unroll the design. So if we add this unroll and then synthesize it, can anybody synthesize it and tell me how much cycles you get? Add this line, synthesize it, and tell me how much cycles you get. Right now, good. Yes, how much cycles you get? How much cycles? 200, 256. How about one? Second. Then somebody answer me that we unrolled the hardware and it actually got slow. Do you understand the problem here? 자, 여러분. 하드웨어를 4배 크게 만들었어요. 덧셈 하는 거를, 4배가 아니라 16배죠. 사이즈가 16이니까. 16개를 넣었는데 속도가 오히려 느려졌어요. 왜 그렇죠? Why is it slower? If you don't know, please take a look into the schedule viewer. Synthesize it. you see, at some point, it's trying to parallelize the addition. But the problem is that if you use MAXI, if you read anything from the memory, it arrives sequentially. Meaning that if you want to read 16 elements, it does not happen magically at once. You get one element by cycle by cycle. Which means that even though you try to parallelize it, because the memory fetching is slow, you can't parallelize it. Do you understand this? Okay. Do you get this? So, how could we solve this problem? So make memory fetching faster. Well, unfortunately, that's not possible because we're not changing the ASI components, right? So what should we do? Yang Yisu, you took computer architecture, right? Can you tell me the pipeline of a CPU? What's the pipeline of a CPU? Or what's the stages there? You have stages. Fetch, decode, execute, and write back. We have the same here. We read, execute, and then write back. But in this case, we don't need decoding. So we can think something like, oh, we can have a 3-stage pipeline here. We read, add, and then store. So if you do pipelining, what should happen? Let's try this, right? What's the pragma for pipelining? Pragma HLS pipeline. Oh my God, it's 48 cycles right now. 48. So do you consider this is good design? Think so. Let's see the schedule viewer. So we have a giant loop. And do you remember the II, the initiation interval? You get it, right? So the throughput is actually inversely proportional to the II, which in this case 2, meaning that we can compute 1 element per 2 cycles. If you see, oh great, we are trying to pipeline this. In the schedule viewer, if you have something looking like this, you have some bars there, it means that you're applying a pipeline. And it seems that it's pretty much working fine. We reduced the cycles from 196 to 48. That's like 4 times improvement. Great. But I have a question, like, can you do better? Can you do this better? So today's homework, I will ask you to write an IP that does the saxpy and daxpy. If you don't know this, it's just like AX plus B. And in the AX plus B, I will require you to compare 2 versions. One is the pipeline version, and the second is the unrolled version, parallel version. And in our case, the parallel version seems to work worse. But let's try to make it better. If the problem is about memory, the memory is too slow. One quick solution is that we can make a buffer. And you know that it's the write that takes longer than the read. So one quick idea is that how about we make a buffer to store the temporal results, and then try to write it at once. So let's do it. We will get rid of the pipeline here. And let's make something like an int cbuff. Size of size. And then instead of directly writing to C, you need to know that this line of code is not actually just adding them together. It's also writing to C, which is causing the problem. So instead, we'll try to make a C buffer and write it to the C buffer. And then we'll write the results. And also, we would like to rule this. The lectures, they actually learned about three problems related to data flows. And there's one problem that we haven't used it yet. Any idea what? Any idea what? Oh, my bad. I think I should have made that mistake. Sorry. So do you remember that if we use the unknown, it was 250 cycles. But just by using an additional buffer, we can reduce it to 61 cycles. Right? And there's one program we haven't used it yet. I'm not sure if it decreases the cycles, but we can actually use something. HLS data flow. The HLS data flow will actually pipeline the two for loops. So if you go to the analysis, this version, gosh, this is too big. So once we complete reading, you see that we are actually adding simultaneously. This is actually the performance advantage. And then we are writing it once. And we can also improve this further by using the data flow. Oh, we reduced one cycle, 50 cycles right now. But anyway, we got it better. So it seems that the HLS report is reporting some cycle numbers, but if you, at your homework, you actually see the runtime, it will be far slow than 60 cycles. So 60 cycles, this should be around 100 megahertz. 60 cycles in 100 megahertz is about 60 microseconds. Sorry, 600 nanoseconds. But if you actually use Python, it will take around microseconds. This is a lot slower. Why is that? Because the HLS simulation does not take account of the DRAM latency. So this is a scenario where all the DRAM and interconnect is doing its job without any overhead. In reality, you never know when the DRAM will give you the data. So that's why I want you to do as a homework to compare the pipeline version and also the unrolled version and try to see if actually which one's better in terms of systems. Do you get it? So before we actually make a block design, I would like to explain about the HLS generated designs. Our first one, the one we had no progmas, we have no parallelization, and we have no pipeline. It's just something like you have an AXI, AO register, you get one data, a single scalar value, actually two for A and B, add them, and send it to AXI, which is C, right? If we add a pipeline, what happens is that you can compute it during reading and writing. So pipeline does not actually change the parallelization, but meaning that you can overlap these three stages. However, if you use a row, so we didn't necessarily wrote a factor, but so the usage is HLS, progma HLS unroll factor equal to 16. But if you do not write the factor, it will just try to unroll it perfectly. So in this case, we have 16 of this. 16 of this working in parallel. But the problem is that you can parallelize this stage, but you cannot make multiple AXI interfaces. That's why if you just add a row, you will have a design looking something like you have an AXI, and you have to kind of send it 16 times. You have 16 registers for A and B, and you have 16 adders, and you're trying to write it once, which is why it is slower. And how can you solve this? Just by adding a C buffer. And actually, there's one caveat that the C buffer, so 2 weeks later, we will talk about DRAMs and multi-ported SRAMs. So in our case, the C buffer is not optimized. That's why it seems to look slower than the pipeline version. But today, we're not going to talk about that. But today's key point is that you can use pipeline, unroll, and data flow, or all of them together to try to make a better design. Do you get it? Any questions? If you do not understand anything, tell me right now. Yes. 여러분 사실 I'll just explain in Korean this time. read보다 write가 돼요. 이거는 스케줄 뷰어를 보면 write에 막혀갖고 우리가 언로를 해봤자 결국에는 빨라지지 않는다는 사실을 볼 수 있어요. 오히려 느려지죠. 254. 그럼 어떻게 하냐? 얘네들이 먼저 끝나거든요. 그러면 얘네들이 C 버퍼란 곳에 다 쓸 때 동안 기다리고 다 적었으면 한 번에 쓰자는 거예요. 한 번에 쓴 거를 팬시한 용어로 burst라고 불러요. If you actually add in data flow, you can see in the logs that it's automatically making a burst request. Do you have it somewhere? inferring burst right. You see? If you use the Karma data flow, it will automatically try to make a burst request, meaning that we will buy 16 write requests and try to write it at once, which is the reason why it makes write requests fast. And you can also see that even though I haven't talked about DRAMs and multiple designs, it automatically tries to partition the arrays even, meaning that it will allow us to write multiple elements at the same time. So these kinds of topics we will talk about later on. But today we'll just try to learn about how to use unroll pipeline and data flow. And that's the reason why it gets faster. Is it clear? Okay, another question? Yes. C is an interface. That's not actually inside your IT sheet. C is an NAXI interface, right? Even though in a plain C code it looks the same, but C is actually an interface, and writing something to C is meaning that you write something to the VMAN. However, CBUF is actually implemented as an SRAM or a register or an actual hardware space where you can store data. That's the difference between C and C buffer. 자, 여러분, 그냥 평범하게 시간 썼을 때랑 HLS 썼을 때랑 결과물이 달라요. C에서는 그냥 C 버프에 쓰든 C에서 쓰든 똑같지만 하드웨어에서 C 버프를 별도로 만들면 실제로 하드웨어 공간 안에 SRAM처럼 내가 데이터를 집어넣을 공간이 생겨요. 그리고 보통은 these kind of SRAMs are a lot faster than the linear interface. That's why we see an improvement in our speed. Is it clear? Great. Question? No? You understand everything? True? Okay. Are you done? So, imagining everybody has understand this. Can you make a block diagram yourself? No. Can you make a block diagram using this yourself? So, it seems that our IT is working. Make an IT and make a block design yourself. And Vivado. Let's start it. Make it. Yeah. 이거? 이게 무슨 말이야? 아니, 내가 Start making your IP design right now. Give me a second. I'll just show you the source code. Okay, if you ever succeeded in making the top diagram, hello, everybody. If you think you're done, let me know. Yeah. Okay, so it seems that some of the students actually succeeded in doing this yourselves. If you have successfully made it, you should see something like this. Hello, guys. Do not forget to make two interconnects, okay? Do you understand? We need two interconnects. One for this and one for that. We have two ports. We have first the AXI light and second the master AXI, which means that you need two interconnects, okay? Okay, the reason I have asked you to do it yourself is that since we have the slave AXI and the master AXI, you actually need two interconnects, one coming from the CPU and the other going to the CPU. You get it, right? Okay, that was the reason. If you had make it, so can you proceed? Can you move on? Can you move on, or do you want to do it yourselves? All right, let's move on. 98. Okay, guys, let's start. What should we do? Hello, everyone. If you want to do your homework, I strongly recommend to watch the screen right now. 자, 여러분 과제 하고 싶으시면 지금 화면 보는 걸 강력히 추천드립니다. We have used this, right? Because we are using an array, we need to use allocate. So if you go to allocate, we can say that, oh, our IP is overlay. Something like this. We see the IP, we have v at 0. Nice. Let's call our v at HW is ip.v at 0. And inside v at 0, we see some MMIO and whatever. And as we have learned how to use the SAXI last week, what do we have? We have an address map. Register map. Yes, we have a register map. Oh, so in the register map, do you remember we have made it a slave bundle port, right? Because we have the MAXI, we have additional slave SAXI light port, which we are gonna use to transfer the pointers. So these ABC, in reality, these are array pointers. And we also have the AP start signal. So we can just initiate when to start this. So let's try this. So first, since we need to make some arrays, let's just create some dummy signals. I don't know, something like so the size of the array will depend on your design. In my case, it's 128. If you made it 16, it should be 16. Oh yeah, we have it. So we have A and B. I think they're both working. So then, just like the FFT example we have done before, we will gonna create 3 buffers.
And remember that we made the design and inserted too. Oh, sorry. Hello, Mike. I think it's working. Yeah. Don't worry. Yeah. And then what you need to do is that we see some element inside A buff. We see something inside B buff, and we should probably see the C buff should be empty. Okay, great. So if we were programming in C, it is very, very super easy to find the pointer of an array, right? But how do we figure out the pointer of an array in Python? Well, you don't. You don't have any method to do that. So that's why we actually have the allocate thing. So if you ever created an array using allocate, you can actually tell the physical address of it. So remember that we should transfer the pointer to the hardware. So what I will gonna do is we add HW dot register map dot A, which is actually the pointer, and I will just put the value of the pointer to the A above, which is the device address, something like this. And we're gonna do the same for B and C. And if we see this, we have some actual pointer value here. If you're an operating systems guy, this will be the virtual memory of the array we have just created, right? Okay, so just like the FFT example, if we look CBUF, what should we have? We should have zeros. Why? Because we didn't run it actually. So if we were to actually run the design, which I know some students have done it in the previous assignment, what should we do? We turn on the AP start. So these are the control signals, which tells you that the AP is on idle, which means that it's doing nothing. So let's say, hey, please run the hardware IP. And how can you do that? We can do that by add HW register map what was it? CTRL dot AP start is valid. Let's run it. And let's look CBUF. Okay, great. It's working. So in the assignment, I want you to measure the runtime. And question, how do you measure the runtime? So in the DMA example, you had a method called wait. So in this case, how do we wait? The only way, if you ever made the block design, you should see an interrupt signal, right? So you can actually choose to make an interrupt controller in your hardware to do this, but I'm not going to do that in our class, but instead, if the IP has done working, it will let the user know by enabling the AP done signal. Or you can just look upon the AP idle to see. My point is that you need to make a while loop until it waits until the IP is done. Do you understand? That's the only way you can correctly benchmark the timing of your IP. In your homework, I will first required you to implement a saxpy operation, which is single precision AX plus B. You have two arrays multiplied by a scalar constant and then add them together. And you should make it in a vector add fashion. And you will have two designs, one pipeline, one unrolled. And you measure the runtime and change the vector length and write in your report why one is faster and how can you make it better. You understand? To be very, I know this is embarrassing to say, I was actually busy, so I couldn't prepare the assignment yet. I'll upload it tomorrow, I promise. Okay, so guess we're done today, right? Great, any questions about the assignment or the code or anything else? I'm here. If you want to enjoy the school festival, go as you want. Yes. 자, 여러분, 그 AP 컨트롤 넌 저번에 기억나요? 그러니까 스칼라 애들 때는 AP 컨트롤 넌을 해서 이 시그널들을 다 없애줬어요. 이 시그널들을 없애주면 자동으로 시작하고 자동으로 끝나잖아요. 근데 벡터 헤드 같은 경우는 오래 걸려갖고 언제 끝날지 몰라요. 그래서 사용자가 직접 언제 시작하고 언제 끝난지를 알려줘야 돼요. 그래서 맨 마지막에 보면 이렇게 돼 있죠. 혹은 we can do it the same as the last week. We can just use it right and find out the address for each register and manually put the values. Okay? We say AP start is 1 and it will start. 아이들은 아무것도 안 한다는 뜻이고요. ready는 돌아갈 준비가 돼 있다. Yes. Sure, yes. In the homework, you should make, just as the same week, make a new example doing saxpy. Which is basically this. Wow, you have an N way to do saxpy? Oh my God, but anyways. This one. We don't have class next week, right? Instead, we will give you extra homework, which is this. If you don't like this, we can do a lecture next week. Okay. Any questions?